Thank you for the kind introduction. I will start my presentation with a brief introduction, and then we'll switch to the material and methods part. And finally here, we go to the results about the pencil testing and about the fracture toughness of these materials, 2024 plate material versus 2024 wire arc DD material. So for the introduction, basically, there are two families of aluminum alloys in airplanes, 7,000 alloys for upper wing parts where we have compressive stresses, and 2,000 alloys in lower wing parts where we have tensile stresses. And basically, the 2,000 alloys combine high strength with high damage tolerance. And the idea is that we apply wire arc additive manufacturing to use the higher flexibility of the process and also for repair purposes. But there is one problem for these alloys. They are both highly susceptible to solidification cracking. Anyway, we did it, and we used the ABB robot with the tilting rotary table for the processing, Fronius CMT power source with the characteristic cold metal transfer, or CMT in short, argon as the shielding gas, and the interface temperature 100 centigrades. As mentioned, these wires are very hard to process, therefore they are not available on the market, and we had to produce our custom-made wire by ourselves by hot extrusion. As mentioned, we used cold metal transfer as a process, and basically we have two process phases for this cold metal transfer: a hot process where the arc is burning and the wire is melting, and a cold process where we have no arc and the droplet transfer is assisted, assisting by a wire movement. And because we have this cold process phase also here in CMT, we reduce the heat input and can reduce the heat accumulation in the previous layer, and therefore CMT is quite often used for additive manufacturing procedures. The materials in the study, we used 2024 plate material T351 as delivered as the reference material, then also in the T6 artificial aging condition, which includes solution heat treatment, quenching, and artificial aging. Furthermore, the 2024 wire arc DD material in the as-built condition and in the same T6 artificial aging condition. And here we have such a 2024 wire DD wall. Furthermore, here in the table, we can see the chemical compositions of the materials. So the plate material and the wire arc DD material. Basically, we have copper, magnesium, and manganese in it. With one major difference, we have also titanium in the wire arc DD material as the grain refining element. Here we can see the build-up strategy for the wire arc DD wall. Basically, we have an alternation of the process direction with every layer, and also we did apply a weaving movement to get broader walls for the milling process afterwards. Here we have an overview of the final microstructures. On the left side, again, the wire arc DD material with an average porosity of 0.4%. And here we have the Barker edge conditions of this material. We can see that we have kind of a wild microstructure. We have aqueous grains, we have elongated grains with different directions also because of the process strategy. So very inhomogeneous. And on the right side, we have the microstructure of the rolled material, which is directed into the rolling direction as we would expect from a plate material. For the fracture toughness study, we used an Instron 8872 testing machine and CT samples, as we can see here on the right side, W16 and B5.5, according to the standards 647 and 1820. Furthermore, for the 2024 plate material, a side grooving was necessary. And here in this picture, we can see the orientations out of the raw materials. So the process direction, according to the process direction for the wire arc material, and according to the rolling direction for the plate material. So we have the horizontal orientation, and perpendicular to it, the vertical orientation. now we switch to the results. Let's start with the tensile tests. On the left side, the blade material in the conditions T351 and T6 with both vertical and horizontal orientations. Basically, we have one difference in the material or in the conditions, the reduction of the fracture strain from T351, which is about with a fracture strain at 22 to 26%. In T6 condition, we only have 14% fracture strain here. On the right side, we have the YRDD material with the two conditions as built and T6. For the orientations, again, vertical and horizontal, we can see that the strength in the built condition is quite low, but this can be improved to a similar level, let's say, in the T6 condition, but we have also a high level of anisotropy. And furthermore, we have to mention that here the fracture strain is on a different level, quite low, for 0.5 in the vertical T6 sample and 6% in the horizontal one. So different level of fracture strain, but this is similar to other works on 2024 YRDD material. Now we go to the fracture toughness of the 2024 material, plate material. We have here all the resistance curves in this diagram, and we have the T351 resistance curves in the upper region and the T6 R curves in the lower region. That correlates great actually with the tensile tests of this material because the fracture strain is also reduced. And furthermore, we can see that in the vertical orientations, we have a higher fracture toughness for both conditions than in the horizontal orientation. Here we have an evaluation of the crack deflection for the plate material in the condition T6 and T6 horizontal and vertical. We can see that we have rather a flat crack, a straight crack propagation with below 1 millimeter for the whole sample here. And in the SEM, we can see that we have basically intergranular and transgranular regions with dimples in the transgranular regions because we have a quite high fracture strain in this material, but also with some coarse particles on the grain boundaries. In the EBSD mapping, we can see that it seems quite easy for the crack to propagate along the grain boundaries here in the horizontal specimens. Sometimes the crack also has to go across the grains, but in the vertical orientations, it's quite hard for the crack to propagate through all these grains, and therefore the resistance against cracking is higher here for the vertical samples. The fracture toughness for the YRDD material is a bit different. So we have here again all the resistance curves for S-built and T6 conditions in both vertical and horizontal orientation. But we have more like of a mixture. We have a higher scatter of the specific results. We have no clear anisotropy here visible. And also it is quite similar, the fracture toughness results for both the S-built and T6 conditions. So we are about 30 MPa root meters for both materials, for both conditions. The evaluation of the crack deflection also looks a bit different here because it's much higher. So we have about 2 millimeters in the horizontal sample and 1.5 millimeters in the vertical sample, which basically comes from the process strategy with the weaving movement. In the SEM, we can also see intergranular and transgranular regions, but we can furthermore see some defects like pores in the material and also some particles at the grain boundaries. And in the SEM, again, we can see our wild microstructure with aqueous and elongated grains. The crack basically goes along the grain boundaries. Doesn't really matter if we have aqueous grains or elongated grains, but the crack propagation is controlled by defects such as pores and micro shrinkages on the grain boundaries for both orientations. And here in this area, yeah, we can see that the crack is within one DD layer, so it is not along the melt-pool boundaries. Here in this upper region, we can see the melt-pool boundaries from the layer-by-layer processing. And furthermore, with the tilted lines, we can also see the melt-pool boundaries from the weaving movements. Finally, here, the diagram with all the mechanical properties here of this study. So we have on the left side the plate material, on the right side the wire arc DD material. We know and we see again that the mechanical properties of the plate material is higher, especially the fracture strain. On the other side, for the wire arc DD material, we have a lower strength in the spill condition, which can be improved for the T6 condition. And we have a low fracture strain for all these conditions, especially in vertical direction. But the fracture toughness is on a very constant level of 30 MPa root meters and is not so far from the T6 condition of the blade material, which is about 40 MPa root meters. So what's next? Basically, we have to improve the microstructure, get rid of the pores and the micro shrinkages at the grain boundaries to improve the mechanical properties, especially the fracture strain and also the fracture toughness finally. So thank you very much for your attention.